Okay, kids, we are in chemistry. We are in module 5, and I've got to go ahead and fix this thing so that I can see what I'm recording. But we're in module 5 of Exploring Creation with Chemistry by J. Weil. It's the second edition. But it doesn't matter if you're using this book or not, because the concepts that we're talking about today are very easily transferred right to another text that you're using, because they're just basic chemistry concepts. What we're going to be talking about today is the concept of moles. And no, we don't mean these cute little furry animals that look cute until your parents see them tearing up your yards. But we are talking about a chemical mole. And what a mole is it's a unit of measure. And we simply think about a 100-meter swimming race or a kilogram of sugar. You know, we talk about units of measure. Well, what a mole is in the chemical sense is it's a specific number of atoms that are contained in a unit. That was not particularly articulate. Let me try this again. This is 6.02 times 10 to the 23rd atoms. A mole is 6.02 times 10 to the 23rd atoms. Now let's think about what an atom is. Atoms are the things that are all squished together to make up all of the matter that we have, to make up gases, to make up this book that makes up our body, but atoms are so tiny you can't begin to see them. What exactly does 6.02 times 10 to the 23rd mean? Well, let me show you what 100 million or 600 million looks like. This right here is 600 million. Now think about having 6 million ants, 600 million ants, $600 million. It's a lot to us, but all this is in scientific notation is 6.00 times 10 to the times 10 to the 8th. So you would need to add 15 more zeros onto this number to get this many atoms that are contained in 1 mole of atoms. So all mole is just a unit of measure. A pound, an ounce, a kilogram, a liter. It's just a unit of measure. And all it means is 6.02 times 10 to the 23rd. And you need to have that. You need to understand that when I talk about a mole of something, we're counting the number of atoms. Okay, and we're not going to take a lot of time on this. We're going to sort of have this be chemistry light, or almost a Cliff Notes approach to this chapter 5 right here. Now this number right here, 6.02 times 10 to the 23rd, which is the number of atoms that are contained in a mole, that has a very special name, and this is called Avogadros number. Avogadros number. And no, I didn't say avocado's number, Avogadros number. And you will want to understand that if somebody asks you what Avogadros number is, that's 6.02 times 10 to the 23rd. And this tells us how many atoms there are. Avogadros number tells us how many atoms there are in a sample of an element. Now remember, elements are these things that are listed on the periodic table of the elements. It's a pure substance, an element of sodium only. You know, if you have sodium all by itself, that's in what they call its elemental form. There's nothing else mixed with it. Now salt, on the other hand, is sodium chloride. It's a compound, it's a specific combination of sodium and chlorine. When it reacts together in a certain ratio, you form the compound sodium chloride. But Avogadros' number tells us that there are 6.02 atoms in a specific mass of an element. And this is something that's going to be extremely important to us. So let me go ahead and rewrite this up here and make sure that I can see it. Yes. Avogadros' number. Okay. And I'm reading this directly from page 146 of your test. It's 6.02 times 10 to the 22, and it represents how many atoms are in a sample of an element when that sample has the same mass in grams as the element's mass in AMU. So let's just take this apart and see what we have. First off, it's 6.02 times 10 to the 23rd atoms. So we have there are 6.02 times 10 to the 23rd atoms in a sample of an element. In a sample of an element. It looks like I have it all run together. Sample of an element. Let's just say that right in here, this contains the element AU. And if you, let's see, is that drawn there? Yes. If you look in your table, periodic table of the elements, and you're going to find AU, and that one is, so how come it's not here? It's because it's gold. It's number 79, there's 43, there's 79. The number that is right above the AU in your periodic table of the elements, that's its atomic number. Here's a symbol for it, AU, which is from the Latin for gold, and the number beneath it is 197.0. And that's what we call its atomic mass. And we learned that an atomic mass unit just a little bit earlier. Got to get back to where I am in this book to tell you what an AMU was. An AMU is 1.66 times 10 to the minus 24. 10 to the minus 24 is like a trillionth, 1 trillion trillionths of the weight of a housefly. But anyway, this is the weight of a molecule of the element gold. So it's so teeny tiny because you can't see an atom, but there's a specific weight to it, and it's an atomic mass unit, which is a trillion trillionths the weight of a housefly, something that's you can't even begin to weigh in a way that's meaningful to us. But what this tells us is that one atom of gold weighs 197 trillion trillionths, if you will, the weight of a housefly. Now, back to Avogadros' number. There's 6.02 times 10 to the 23rd atoms in a sample of an element. And we're going to have this element right here be gold, where you have the same number of grams of that sample. So we're going to have 197.0 grams of gold. And I'm going to write out gold so that you remember what that is. Gold is AU. Okay, you see this? Yes, we see this. There are 6.02 times 10 to the 23rd atoms in this container of gold that has a mass of 197.0 grams. This contains 6.02 times 10 to the 23rd atoms of gold. Okay. There are 6.02 times 10 to the 23rd atoms in a sample of an element in grams. With the weight in grams, it equals its weight in AMUs. In a sample of an element with the same mass in grams, as that element's mass in AMUs, with the same mass in grams as the element's mass in AMUs, atomic mass units. Wish I had different color markers with me to help highlight and point out things. I'm going to keep saying this over and over and over, repeating it. Avogadros number is just a number. Avogadros number refers to 6.02 times 10 to the 23rd. And that tells us the number of atoms of a specific element that are contained in a sample of that element. When we talk about a sample, all we mean is an amount of that element. But the weight of that sample, mass, the mass of that sample is going to be measured in grams. And the grams of that sample has to be the same as the element's mass in AMUs. Well, how do you find out what the mass of an element is? You look at your periodic table of the elements, and right down here we've looked at AU for gold. The number at the top was 79. The number below this symbol AU was 197.0, which told us the mass in atomic mass units. So we have, instead of 197 atomic mass units, we can't, but we can take that weight, that mass rather, in grams, 197.0 grams, and know that this sample right here has 6.02 times 10 to the 23rd atoms of gold. And what this is doing is it lets us count atoms, which tells us the size of an atom. So let's look at, for example, magnesium, which is element number 12. It has an atomic mass of 24.3. So if instead of gold, we had a sample of magnesium, so here's our sample of magnesium, which has an atomic mass of 24.3 AMUs. So we're just going to say 24.3 grams of magnesium contains Avogadros number of atoms of magnesium. Well, what if we picked something else? How about carbon, which is what soot is? Let's see what mass of carbon it takes us to get 6.02 times 10 to the 23rd atoms of carbon. Well, carbon is 12.0, is its atomic mass unit in AMUs. So if we have 12.0 grams of carbon, then we know that mass of carbon contains Avogadros number of atoms of carbon. And that's all this is talking about. Now, something else that is really neat that we've discovered is not only does this work for the mass of, for the number of atoms in a mole of an element, it also works for the number of molecules. Now, what's a molecule? A molecule is what you have when you have a compound of something. Remember we talked about sodium chloride, or let's just say water instead. Let me see where I can go. Right here, helium is a homonuclear diatomic. A homonuclear diatomic means that in nature, when you have the element helium, it's not just one atom, one atom, one atom, one atom, but this helium occurs in pairs, diatomic. Remember, di is 2. So here we have a helium, here's a helium, here's a helium, and there are 2 helium atoms that are bound together with a specific bond that we'll talk about later. So this would be, if we have with helium having an atomic mass of 1.01, if we had 1.01 grams of helium, there would be Avogadros number of these helium atoms. They're diatomic. They're 2 atoms hooked together. Now, let's say that we reacted helium with oxygen. H2 plus O2 is going to give us water. So we now have H2O. So we have a helium and an oxygen and a helium, and we have a helium and an oxygen, and we have a helium, helium, oxygen, helium. So these are not atoms because they contain pieces of more than one element. So when you have more than one element, which is hydrogen and oxygen, when you have more than one element together, these are called molecules. So there are 6.02 times 10 to the 23rd molecules in the sample of an element. No, this is not an element because it contains 2 different elements. So it's in the sample of a compound. This was atoms, but we're going to change that. Avogadros number of molecules in a sample of a compound with the same mass in grams as the compound's mass in AMUs. As a compound's mass in AMUs. Now let's think about this. And let's go ahead and use this example of water and hydrogen. If we had hydrogen, there are 2 atoms of hydrogen that are hooked together here. So the mass that we would need of hydrogen, if one hydrogen atom has 1.01, we'd have 1.01. 1.01 is 2.02 grams of helium would contain Avogadros number of atoms, or even more than that. You have carbon. Carbon has an atomic mass of 12.0, so you have all of these little carbon elements, carbon atoms floating around. And if you had 12.0 grams of carbon, that would contain Avogadros number of atoms. Now, let's say that we have water hanging around here. H2O, 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 and it says if we have, we know that we have Avogadros number of molecules in a sample. When the sample weighs the same, when the sample has the same mass in grams as the compound's atomic mass. So what is the atomic mass of H2O? Well, you have 2 atoms of hydrogen, so it's 2 times 1.01 plus the atomic mass in grams of oxygen, and oxygen is 16.0. 2 times 1.01 because helium has an atomic mass of 1.01 units. There are 2 of those, so we have 2 times 1.01 plus 16.0, which gives us 18.02, a sample of water that has a mass of 18.02 grams is going to contain Avogadros number of molecules, which is 6.02 times 10 to the 23rd. That's what we're talking about when we talk about Avogadros number. And you see that the mass of an element or the compound that you have that contains this many Avogadros number of molecules is going to be different. It's going to depend on the atomic mass of each element. It's going to differ with the atomic mass of each compound. So let's go ahead and look at example 5.6. And let's work through this one. And I'm going to finish this sample, and I'm going to go up and see if I can get another eraser, because this is fairly pitiful here. Should have gone ahead and brought my own orange cloth eraser. Question here says, how many moles of fluorine, did I skip the page? Nope. Now let's see, how many moles of fluorine atoms exist in a 50.0 gram sample of fluorine? So we have 50.0 grams of fluorine. That's not fluorine, it's fluorine. And that has the abbreviation of FL. How many molecules? Rather, how many atoms, because it's an element. Molecules are compounds, atoms are elements. So what do we know from Avogadros number? We know that if we have 1 mole of fluorine has how many molecules? Sorry, how many atoms? Well, it's going to contain Avogadros number of atoms, 6.02 times 10 to the 23rd atoms. But what's 1 mole of fluorine? How are we going to know what 1 mole of fluorine is? You're going to look at your chart. You're going to go to fluorine, see how quickly I can find it, which of course I'm not finding it fast now when I want to. Fluorine is element number 9. It's because it's not FL, it's just F. 1 mole of fluorine, the atomic number is 19. The atomic number is 9 for fluorine. Its atomic mass is 19.0. Okay, so what does this tell us? This tells us that if we have 19.0 grams of fluorine, that's equal to 1 mole. So 19.0 grams of fluorine is equal to 1 mole. If we have 50.0 grams, 50.0 grams should be a small g of fluorine, how many moles is that? We cross multiply. 19.0 x grams and moles, I'm going to write all of this, is equal to 50.0 grams times moles. Okay? What are we solving for? We're solving for x grams. We want to find out how many grams. So we're going to divide this side of the equation by 19.0 moles. We want to divide the other side of the equation by 19.0 moles. What are we going to have? 19s cancel, moles cancel. And 1 mole, 19 grams, 50 grams. So we have X grams. How many grams? Is equal to 50.0 divided by 19.0. And that is going to give us, actually we don't want to find out how many grams it is, we want to know how many moles it is. So we're going to divide by grams, not by moles. That was my problem. Moles, going to divide by grams. Going to divide this side by 19.0 grams. We could go back through and divide out all of these units evenly. What you're all doing is there's a relationship for every 19 grams, that's 1 mole. So for every 50 grams, how many moles is that going to be? 50 divided by 19.0 is 2.63 moles of fluorine. Moles of fluorine. We're looking for relationships between masses and between numbers. Because we know that no matter what element, no matter what compound we're talking about, we know that 1 mole of that has to contain 6.02 rather, times 10 to the 23rd atoms, or 6.02 times 10 to the 23rd molecules. And the size of that sample is the size, has to have the same mass in grams as the element's atomic mass, 19.0, or of a compound's atomic mass. And if you've got a compound, like here, calcium carbonate, I think, you have to calculate the mass of calcium. Well, you have to look on your chart for the mass of carbon for 3 times the atomic mass of oxygen. So let's go ahead and do that one right away quickly. Calcium is 40.1, carbon I think is 16, carbon is 12. Calcium is 40.1, carbon is 12.0, oxygen is the one that's 16, but it's 3 times 16. So you have 40.1 plus 12 plus 48.10. You would have to have 100.1 grams of calcium carbonate when you had that amount of the sample of this compound. That would contain 1 mole of molecules of calcium carbonate. So that's the end for this particular section.